All right, so welcome to this AI4OPT seminar. So I'm super delighted to introduce Vijay Ganesh. I met him the first time when he was at Waterloo, but Vijay has a very distinguished career. He has his PhD from Stanford, spent some time at MIT. He was professor at the University of Waterloo for many years. And one of the things which is interesting about Vijay is that he does two interesting things. So one of them is building this SAT solver. He's been this, SAT modular theory solvers and so on. And he's probably one of the world leaders in that space, surely one of the world leaders in that space. But he also do theory and the results in decidability and computation and computational complexity. So it's like a mix of both theory and practice. He has many awards. I'm not going to go through them, but test of time awards in a number of different areas. So we are super excited to work with Vijay on different projects right now. He works on a very interesting topic, and I won't say more, Vijay, but thank you for doing this with us. And the floor is yours.
Thank you. I'm truly honored that you've given me this opportunity, and all of you are here. So today I will be talking about a particular way of thinking about combining machine learning and automated reasoning, which are two big sub areas in AI. And by design, my talk is a little bit high level. So I'll not necessarily go into like massive amount of detail. My goal is to connect with as many people who can use this type of combination to solve their problems. So I think it goes without saying that reasoning and learning are two big areas in AI. And when I use the term reasoning, I mean something very particular. What I mean is a system that is rule-based, that is using rules to come to some conclusion, some deduction. And by learning, I think we are all sort of familiar with learning. The goal is to learn some function from data, right? So these are two big areas in AI. And I start from the assumption that these two areas have largely been separate, although I was just informed 5 minutes ago that my assumption is incorrect by Pat Langley over there, and that people have been doing neurosymbolic AI for a long time. So I will change my tack a little bit and say that I'm actually talking about a very specific way of combining learning and reasoning. Okay, so why combine learning and reasoning at all? Actually, the argument in favor of combining learning and reasoning became much easier over the last 2 years. Why? The reason is we have generative AI, and people are using generative AI to generate code. People are using generative AI to generate mathematical proofs. People are using generative AI to generate molecules, drugs, theories of physics, etc. How do we know that these objects are correct? What does correct even mean? What is the meaning of the word correct within this setting? And so I will define that notion of correctness, and it'll differ depending on the context. But once you start thinking about the use of generative AI to generate, now let me use the term formal objects. By formal, I mean that things that are well-defined, like mathematical proofs, computer code, a molecule, theory of physics. These are formal objects which can be analyzed symbolically through an automated reasoning tool. And so now the next question is, okay, you have a generative AI model that is generating these formal objects, and people are using it at scale now. Like, for example, Cursor is being used everywhere these days. Many of you are probably already using Cursor. So if LLM is doing a fantastic job, why even worry about checking the correctness of what it is outputting? And the answer is that LLM is not quite doing a fantastic job. Yes, the code generated looks real nice. The proof generated looks cool, but LLMs hallucinate. They have logical inconsistencies in their output, and they produce errors that are very subtle. Security errors, for example, that you do need to check. There is one more motivation. Another motivation is that just not only the fact that LLMs are being used for code generation and sort of very practical things, but also in the setting of mathematics. There is a big DARPA program right now called Exponentiation of Math. And the DARPA program is all about how do we have an AI system which will essentially be a tool that mathematicians will go to prove theorems that they couldn't prove otherwise, or come up with counterexamples they couldn't come up with otherwise. And now we have also the notion of agentic AI, where the LLM can call out other agents, construct a plan, and fill things out, and so on. So within all these settings, it makes sense to combine LLMs and automated reasoning tools. Now, I started in this business of combining automated reasoning with machine learning about a decade ago, and it was very difficult for me to convince my automated reasoning colleagues that they need to pay attention to machine learning. And the machine learning colleagues were like, nah, we're the automated reasoning, I'm not talking to you. Okay, so that was the situation. But now people are very excited about this combination. So given the natural reason as to why we need to bring these two fields together, the story becomes far more compelling than it used to be. Just to give you a very quick overview of where I'm coming from. So as I said earlier, my core focus is automated reasoning tools. And these are, as I mentioned earlier, are rule-based systems. So the best way to think about this from an input-output perspective is that these kind of tools take as input mathematical expressions, formulas, theorems, and so on, and produce as output either that statement that you give as input is true, and in which case it'll produce a proof for it, or it'll come back and say the statement is not true and produce a counterexample. The best such tool that I work on is SAT solvers, which take as input conjunctive normal form Boolean formulas and decide their satisfiability. So I've built a variety of tools in my career, which have been applied broadly in the context of software engineering, security, and mathematics. I won't go into it in great detail. I just wanted to let you know that this is where I'm coming from. Okay, so what is the philosophical origins of this? As far as I'm concerned, started with my work on a tool called MapleSat. And in MapleSat, I'm going to very briefly describe to you how a SAT solver works. And what we did there was we kind of viewed the SAT solver as a system which has two processes in it. One process is a machine learning agent, and the other process is a reasoning agent. So how did we come to that realization? So in order to make that clear, allow me to give you a very quick overview of how SAT solvers work. This is probably the most technical part of the talk, and the rest of the talk will be relatively straightforward. Okay, so what is the SAT problem? I'm assuming everybody knows what the SAT problem is. It's like the most fundamental problem, in my opinion, in computer science. And what is the problem? You're given formulas, Boolean formulas in conjunctive normal form. We say a formula is in conjunctive normal form if it's a conjunction of disjunction of literals, where a literal is either a Boolean variable or its negation. We know that this problem is NP complete, and we believe that it is in general intractable. So the goal of the SAT community is to build practical SAT solvers that work well in some scenarios. Obviously, these SAT solvers we already know lower bounds for them, meaning that there exist classes of families of formulas for which these algorithms will take exponential time. Okay? And why is it such an important field? The reason is that I started working in the SAT SMT space in the late 1990s, and people would tell me at the time, given that we believe P is not equal to NP, efficient SAT solvers for practical applications don't have a right to exist. But they do. And that's what we have done over the last more than 2 decades. And there has been 1,000x improvement in the performance of these SAT solvers, meaning that we can solve formulas today with millions of variables and clauses in them that are highly non-trivial, right? But again, this does not, there are also formulas that these solvers will fail on, meaning they will take exponential time, where such formulas will only have a few hundred variables. So both our statements are true. But the value addition here is that as SAT solvers are improved in performance, it has opened up completely new applications for us within the broader software engineering context. That's where I was coming from. So my goal, I was building SAT and SMT solver with the specific goal of formal verification, but over time also testing, program analysis, program synthesis, etc. Okay, so every time you have a 10x improvement, suddenly new things become possible. And today, the biggest application is trustworthy AI. And I would include theorem provers, like first order theorem provers, higher order theorem provers such as Lean, Isabelle, Koch, etc., as a richer version of what we are trying to do. Okay, so how does a SAT solver work? Okay, so when I use the term SAT solver, I'm referring to a very specific class of algorithms called conflict-driven clause learning SAT solvers, which were invented about 30 years ago. Here is how it works at a very high level. It takes as input a formula in conjunctive normal form and decides whether or not it has a solution. Okay, if it has a solution, it'll produce a solution. If it does not have a solution, then it'll produce a proof of unsatisfiability. If a formula does not have a solution, we call it unsatisfiable. If it has a solution, we call it satisfiable. So the first step in a SAT solver is what's called as propagation or Boolean constraint propagation. The idea is very simple. Suppose you have a formula, and in that formula, you have a clause which has exactly one literal in it. Let's call it negation of x. Then if your goal is to decide whether or not the formula has a solution, you have no choice but to set x to false, right? You have to satisfy that particular clause, and then you can simplify the clause with respect to that assignment. Now, when you set x to false, it's possible that some other variable becomes unit. By unit, I mean that only one literal in that clause is unset. So then you have no choice but to make it true somehow, either true or false, right? You keep doing that until you reach a fixed point. By fixed point, we mean that there is no more Boolean constraint propagation to be done. At which point, the solver will check whether or not there is a conflict, meaning that the formula is unsatisfying under the current assignment. If it is unsatisfying under the current assignment, we say the formula or the state of the solver is in conflict. Otherwise, we check whether all the variables in the formula have been assigned. If all the variables have been assigned, we know that the formula has a solution. We output SAT and produce a solution. Otherwise, what do we do? So now, we are in a steady state. We are in a fixed point. The formula is neither satisfiable, nor is it unsatisfiable under the current partial assignment. So then what the CDCL solver is going to do is it's going to somehow magically pick, I'm using the word magically in a purposeful way, but it'll pick some variable, assign it a value, add it to your queue of assignment, and then call BCP on it again, which will give you opportunities to simplify further, right? And you keep doing this until you detect a conflict, because chances are that the assignment that you come up with might very likely, the first set of assignment you come up with very likely will be unsatisfying for the formula, at which point there is a box inside the solver called conflict analysis, which is invoked. And the goal of the conflict analysis box is the following. It takes as input the formula and the assignment under which the formula is unsatisfying, and it then determines the root cause as to why the formula is unsatisfying under that assignment. What does that mean? Suppose you have a formula with a million variables in it, and you assigned 500,000 of those variables, and you determined that the formula is unsatisfying under that current partial assignment. It could be that it was two variables, the variable that you assigned at position 23 and the variable that you assigned at position 450,000, that together are in conflict. That's a core reason as to why that particular assignment is unsatisfying. Now, why should you do root cause analysis like this? The reason is very simple. If I realize that a very small number of variables are the true reason as to why the formula is unsatisfying under current partial assignment, and I remember that, and I don't make that choice in the future, that set of choices in the future, that means that I can exclude or prune away an exponential part of the search space. Does that make sense? So the ideal clause, and this is called clause learning. So this is a deductive process. It's not a machine learning process. So, and in particular, what the conflict analysis box is doing is a technique called resolution. It's implementing a resolution proof system. And then it outputs a clause, which is the negation of the root cause as to why that particular assignment was falsifying for the formula. And it just remembers that. So you remember the mistakes you made. And by remembering the smallest number of decisions that led you to a bad place, you then avoid any extensions of that. And in this way, you prune exponential parts of the search space. Does that make sense? So, I could go through assignment tree to make this point more clear. So imagine for simplicity, you have here the nodes here are variables and edges are assignments to those variables. By green node, we are referring to what we call as decision variables, which are the variables that are decided by this branching heuristic. And the purple nodes are propagations, which are determined by the BCP. And the red node is telling you that that particular assignment is not satisfying for the formula. And if you learn if it so happens that the only reason as to why this million variable path in the assignment tree is not satisfying is the fact that you set X to false, then you just remember that X should never be set to false in the future. You set X to true, and now you have cut the search space in half, right? And this is how you cut exponential search spaces, you prune them away. So basically, you can think of this particular method has essentially two processes in it. One process is BCP followed by branching, and that is this loop. It keeps on going like this until it hits a conflict, and the second process is invoked, which performs reasoning. So we started thinking about this from a reinforcement learning perspective. Here is the idea. So you have one process, which is the decision heuristic and the BCP, which is like an agent, which is searching through the space of assignments. And the moment it hits the assignment that is not satisfying, it queries a deductive box, the proof system, the clause learning box, which is like the environment, but the environment now has logical capabilities, reasoning capabilities added to it. And it analyzes as to why the agent got stuck. And it feeds back a learned clause that tells you a pithy reason as to why that particular assignment failed, and exponentially many other similar assignments are also going to fail. So it tells the agent what to avoid. And the agent takes that as input, it stores that as knowledge, and it analyzes it in the future to decide which other variables to branch on. So in this way, we were able to leverage a lot of knowledge from reinforcement learning, algorithms from reinforcement learning, adapted to this setting. And now when we view the SAT solver in this way, we were able to make it much more efficient, and we were able to come up with the whole design of these kind of heuristics in a much more principled way. Because previously, people were inventing these heuristics in an ad hoc way in the attempt to win the SAT competition. And we said that that's not the only way to do it. A better way would be to use machine learning techniques, which can leverage the data that is generated through the reasoning and use that to make better choices, predictions as to which variable is the best one next to branch on, when to restart, which clauses to retain. And you can do this at many different levels inside the SAT solver. So now once you have this view of things, you can see what's going on here. And when LLMs came online, it became very clear to me that this loop is going to be very productive in that setting. Why? What's happening here is that the agent is producing an assignment, which is a formal object, and the formula together can be analyzed by the reasoning engine. It will tell you the root cause as to why things are not working. It will localize the error and feed that information back to the agent. And if the agent has the ability to process it, then it can make better decisions going forward. Now we can just lift this idea to the LLM setting, and it's very natural now. It sort of makes sense. Now imagine that the agent is generating code as opposed to assignments or proofs. And then you can have a system on the other side, which is going to help figure out where the errors are, localize them, and feed a certificate, a small certificate that characterizes the error with not only the object that was generated, but potentially exponentially many similar or even infinitely many similar objects that have the same error. And if this agent has the ability to process that certificate, then you can prune away that part of the search space and move in a different direction. So that's the key idea. And if you understand that, the rest of it is sort of detailed at this point. Okay, so the rest of the talk, I will talk about a particular extension of this idea called reinforcement learning with symbolic feedback that we have used to apply to the context of code, math, and science. And then we have also applied for in the context of scientific, combining LLMs with scientific simulators for physics and so on. And towards the end of my talk, I will talk about how we plan to combine LLMs with the lean theorem prover, where the goal is to automatically formalize large parts of mathematics. So by formalize, what we mean is we want to go from informal math in textbooks to lean code, and thus populate the lean library. Further, we also want to do proof synthesis and definition synthesis and concept synthesis. Okay. All right, so let me start with this idea of reinforcement learning via symbolic feedback. So the idea is actually very similar to what I just described. And again, the goal is to apply LLMs to complex tasks. For example, tasks like a synthesis of chemicals, code synthesis, etc. And we want to have have an ability to fine tune the LLM in a way that it makes use of symbolic feedback. Now, what I want to emphasize here is that so far, what we have explored is that we are using symbolic feedback primarily for fine tuning, but one could imagine using a similar feedback mechanism in the context of training, also in the context of inference. At runtime, when you're using the LLM to do an inference, you could be getting feedback from a symbolic system, which would then help you do automated prompt engineering. So you will have new prompts that are coming in that are based off of the feedback generated by the symbolic system. So in general, when we publish this, or we actually haven't yet published the paper yet, but we archived the paper about a year ago. This idea of most of the time when people were talking about fine-tuning, it was basically a supervised fine-tuning method. But in addition, people had started using reinforcement learning, but most of this was reinforcement learning with human feedback. Now, of course, with the DeepSeek prover and so on, people are using reinforcement learning in a much more sophisticated way. But and I'm going to contrast what we are doing versus that as well. But let me start with reinforcement learning with human feedback. And the existing methods are essentially trying to get the LLM to generate output that is aligned with human preference. And most of the time here, the human is, who's providing the feedback, is simply saying whether it's a yes or no feedback. So yes, they prefer this output, or no, they don't. But there is, to the extent that I'm aware of, at the moment, RLHF techniques don't provide fine-grained feedback to the LLM. So that's the problem, right? So let me just skip all this. And so here on the left, you have the RLHF method. And on the right, you have the RLSF method, reinforcement learning with symbolic feedback. And the main difference here is the following. Imagine you have a LLM, and you're giving it a prompt. The prompt could be of the following form. It could be some pseudocode as input, and the output of the LLM that you want is a C++ code. And you take the C++ code, the response, give it to the environment, which is a symbolic system. And when I use the word symbolic system, I'm using it in a very general sense. As long as it's rule-based and it's doing some form of reasoning, to me, that is a symbolic system. That could include not only SAT solvers and SMT solvers and theorem provers such as Lean, but also compilers. Compilers are also symbolic systems. Program analysis tools, testers, etc. So in this particular setting, we feed that to the symbolic system. It will figure out what the issue is with that particular generated object and provide symbolic feedback. And the difference between this and RLHF, there are many differences. One of them is that the symbolic system is automated. The second difference is that the symbolic system can provide very fine-grained feedback. It can tell you which tokens were indeed offending and not just give you a yes or no answer. So even in the case of DeepSeek, where they were using reinforcement learning, they were using Boolean feedback. And what we have done is basically modified the well-known PPO algorithm with an extension so we can do symbolic reasoning. And the value addition of this is many folds. One value addition, as I already mentioned, that gives you fine-grained feedback. You, of course, as a user, have to somehow design the reward function. So you're getting this output from the symbolic. So input to the symbolic system is the output of the LLM. And the output of the symbolic system is the potential errors in the input. And you have to design the reward function which takes this input that error that is produced by the symbolic system and somehow convert that into feedback to the LLM. So that is the task that human has to do. Okay, so this is the algorithm, but I won't go into the details of the algorithm and just stay at this level. And in particular, what we did here, so in this specific application scenario, we used RLSF to synthesize code from pseudocode. So the input was, so we got a data set, and here we are doing fine tuning. So the data set was a mapping between pseudocode and C++ code. And so we wanted to fine tune it and help it produce C++ code. So if we give us input this prompt, it produces output C++ code. We would give it to a G++ compiler, and the G++ compiler, along with a test suite, would check what the mistakes are in the code. So the value of a compiler is that it will tell us which token, where the error is, which tokens are offending, which cause that particular code not to compile. And the value of the test suite is, it'll tell us whether or not the output produced functionally adheres to the specification, right? So the specification in this case is your pseudocode. And together, they tell us which particular tokens are offending. And so we designed a reward function which would identify which tokens are offending, and it would give a fine-grained feedback to the LLM. These are the offending tokens. Please go and fix them, right? And this is how we set this up. There was another project that if time permitting, I'll go into much greater detail, but allow me to go through this quickly right now. The goal of this project was to do translation from one programming language to another programming language. So people actually do write transpilers to go from one programming language to another. This is a very common activity, and it is a very painful activity, actually. And often when humans write transpilers, there are aspects of the programming language that they miss, which means that the transpiler would just break. It will, if you were to give it an input, which is a piece of code in Java, which is using a specific feature of Java that is not supported by the transpiler, the output would be error, I can't handle it. By contrast, LLMs are actually, what we notice is that when it comes to software engineering tasks, LLMs are much more flexible. They produce some meaningful output which you can post-process and still give feedback. And if you have the right data set, you can train them, which is a far easier activity than hiring a bunch of engineers trying to fix the transpiler. Okay, so anyway, coming to this, so what is the goal? We wanted to go from Java to Python. Now, our first instinct was, why don't we get a data set where we have Java at an equivalent Python code, like a Rosetta Stone, fine-tune the model on it, and that we would be done with that, right? And the performance of the resultant model wasn't too good. So then the idea was, okay, now let's sort of compile. So we compile the output Python and see what happens. So we were using some compile Python and use the RLSF approach that I just mentioned. That did improve performance to some extent, but not to the extent that we wanted. So then the idea was, well, we need to also test it somehow. So, but how do we test it? Now, here is the difficulty here. In order to test it, I need to translate the test as well. The unit tests that are written in Java, I need to translate them to unit tests in Python. So I'm in a little bit of a trouble in, I'll have to somehow bootstrap the system to be able to do that too. So, and I can't trust the resultant test. So I'm in big trouble. So how do I solve this problem? So here is the solution we came up with. Instead of going merely from Java to Python, we said, why don't I go from Java to Python and Python to Java? So I have two models now. So model A goes from Java to Python. Model B goes from Python to Java. The value addition of this is the same unit tests that I use over here can be used over there. It's the same unit tests, right? I don't have to translate the unit tests. I can be sure the unit tests are correct, right? Furthermore, we used a off-the-shelf symbolic execution tool. I don't know how many people know what symbolic execution is, but it's a very well-known program analysis technique, and I actually did a lot of work on it more than 25 years ago. But allow me to just talk about symbolic execution for a moment. It's a way of analyzing computer programs by which you can start from a computer program and automatically convert the computer program into test cases. Here is how it works. You see, when you analyze a computer program using static analysis, what you're doing there, you're not running the code, you're analyzing the code using some technique which will take the entire program and do code analysis on it. And static analysis is this vast field where people have done a lot of work in that space. But the problem with static analysis, the good thing about static analysis, it scales very well. You know, every compiler has a static analyzer in it. And in fact, many static analysis passes in it. The downside of static analysis is it's not precise. So when its static analyzer tells you there is a bug in line 275, you can't be sure that is a correct thing. By contrast, you can also use dynamic analysis. Dynamic analysis means you have a computer program, you have a bunch of test cases, and you have some analysis techniques that allows you to extract information on that benchmark suite. So how many people have used cache grind or val grind? Or these tools allow you to dynamically analyze your code, right, against a test suite. But there is something in between. It's called symbolic analysis. It's a very powerful idea. Here is the idea. What you do is typically when you run a computer program, you are running it on concrete inputs, right? So if you want to run your Word program, you have to give it a concrete Word file. But what if I give as input to the program symbolic variables? What does that mean? Symbolic variables. Here is what it means. What you do is you take your computer program, you run it on a virtual machine, and the input to the program are just variables. They're not concrete values. And what you then do is, as you're executing the program, you maintain a map between program variables and expressions. And these expressions are in terms of input variables. Does that make sense? So now suppose I'm executing a path in the program. Now I have a map between program variables and expressions. That expression is the value, the computed. And how do I do it? Using the virtual machine. The virtual machine just keeps a mapping of this. Now imagine that I take this path in the program, I conjunct every one of those constraints and give it to an SMT solver and say, find me a solution. What does that mean? It will find me a solution in terms of the input variables, yes, which would correspond to a test input that would take that path in the program. Is that making sense? Now imagine I have an assertion in the code. The assertion says that some variables should not have a buffer overflow or integer overflow or whatever assertion it is. Now I can take that path constraint and the assertion and give it to an SMT solver and say, find me an input that follows this path but violates the assertion. That's a bug. Does that make sense? This is how people use SAT solvers and SMT solvers. This is a primary use case for SAT solvers and SMT solvers. So what we did here was, for the input Java code, we had limited amount of test cases. So then we got a tool, symbolic execution tool, which will generate or populate that test case, test suite here, but we can also use it at the output because it's the same programming environment. And by doing so, we have a rich test case scenario, and we did this translation, and now the feedback signal that both the LLMs are getting is whether the output program compiles or not, and whether it passes the test suite or not. And at the moment, and it'll then penalize the appropriate tokens. Okay. There are issues with this approach, of course. One issue is that when we do the feedback signal based on testing, we are only checking how many test cases passed, but we are not giving additional information. What does it mean for a test case to fail? Can you analyze that and try to localize error with respect to that? We're not doing any of that as yet. Another potential bug here is that it's very possible that this LLM learns the correct mapping from Java to Python, but the other LLM fails. So I don't try to find out which LLM is the erroneous one. I'm giving feedback signal to both of them, right? So again, this is still at a very early stage, but one can imagine how to improve upon this going forward. Yet another application was in chemistry. So here the idea is we applied LLMs with domain knowledge for very important chemistry tasks such as forward synthesis. So forward synthesis is predicting the product of chemical reactions given the reactants. Similarly, retrosynthesis is identifying reactants required to produce a specific molecule. So you give the molecule, you say, how do I get it? That's retro. Forward is, here are the inputs, produce me the right output, okay? It's like program synthesis. Now, why would reinforcement learning with symbolic feedback apply here? The reason is there are symbolic tools available that can analyze such outputs, right? So we take an LLM, we fine tune it, we produce this response in a particular format called smiles. And this RDKit is an open source chemistry tool, which can take as input these smiles format and tell you where the errors are. And then we can penalize the LLM appropriately. And by fine tuning it in this way, we get a much better performance for these chemistry tasks than otherwise. We also applied it to the certain logic puzzles. I won't go into the details here, but essentially the idea was we would prompt it by saying, here is a puzzle. It's called Game of 24. And what is the correct solution? It'll produce some solution. We give it to a computer algebra system to check the solution. And again, we localize the error and provide the appropriate feedback. So as you can imagine, the results obviously are very positive for RLSF. And without necessarily going into too much detail, for example, let me just sort of try to give you the high level point of this particular experiment. What we noticed was RLSF tuned code gamma 2B improved functional correctness by 31.43% over supervised fine tuning for the program synthesis task. Furthermore, what we noticed was we were able to, and this is very important, I think, we were able to take an open source model, which is much smaller, maybe 100x smaller or even 1000x smaller than some of the closed source model available at the time, and still outperforms it. So in other words, providing symbolic feedback with reinforcement learning, you could take something that is not great, but small and open source, and make it much, much better as a result, and be able to compete with these larger models. Okay. So similarly for molecule generation, RLSF improved the exact match by 8% and the validity by 58%. And it using the Meta's Galactica 1.3B. Now things are moving so fast in the space that this is already ancient news, these kind of LLMs. But anyway, it was surpassing GPT-4, which is 1000x larger. Okay. So and similarly for the game of 24, right? So the takeaway here is that when you train or fine tune your model with feedback from symbolic systems, and if you're able to produce the appropriate kind of certificate from that model and construct an appropriate reward function to the LLM, the resultant tool is significantly more performant. And not only that, you can fine tune a much smaller model and get similar performance as some of these largest models out there. Okay, so other areas that where we are applying this is trying to discover new theories of physics. So one particular topic there is quantum field theories. Now, I'm not going to pretend that I'm an expert in quantum field theory, but fortunately, I'm working with lots of excellent people at the Lawrence Berkeley National Labs who are indeed experts in this space. And it so happened that I was visiting Simons Institute of Theoretical Computer Science in Berkeley, and I got an opportunity to go and give a talk at the Lawrence Berkeley Labs. I gave this talk, and I talked about RLSF, and a person in the audience says, I was thinking about the same thing. I actually wrote a proposal. I call it reinforcement learning with physics feedback. Do you want to collaborate? I said, yes, I want to collaborate. I want to learn as much as I can. So what is the problem? I know what the problem is, so let me at least state the problem. So here is the problem. You see, quantum field theory is one of the most successful theories out there, but there is a bug in it. What's the bug? We know of the existence of subatomic particles called neutrinos. And physicists empirically have determined that neutrinos must have mass, but a very tiny mass. However, the standard model predicts that the mass of neutrino must be 0. So there is a bug. Can you fix the bug? That's the question. It turns out that you can get different quantum field theories based on certain parameterizations. So if I change the parameter setting a little bit, you get different theories and they have different predictions. So you want a parameterization that gives you the correct predictions for everything, not just for the neutrino problem, but also everything that was known to be correct previously. That's a search problem. I'm searching through a space of parameters. And I can have an agent that parameterizes the quantum field theory appropriately. I can give it to a physics simulator, it does its thing, and provides me a feedback. Same idea. And I can prune the search as well. Back to, if I can find the root cause, then I can prune the search. And it's the same idea. So we are doing that, and so I'm super excited about this project. And we call it certification-driven reinforcement learning because there are some additional techniques on top of reinforcement learning with symbolic feedback that I presented so far that we are using there. Okay, so I'm getting towards the end of my talk, and actually let me just skip this part because I talked about this a little bit, and let me talk about this, which I'm super excited about. This is future work, but I think we are at a point where a lot of math can be automated, and I think it has the potential to have a huge impact on all of mathematics. So what do I mean by that? The goal here is to combine large language models with symbolic systems like Lean for two or three, I should say three main tasks. The first task is proof synthesis. So what do I mean by that? So as input to the system, you give a sentence or conjecture in natural language, and you ask the system to generate a proof in formal language, for example, Lean. Okay? So that's goal number one. Goal number two is auto-formalization. You give us input to the system, natural language, and as output, you want to translate that natural language into formal language, and in this way, populate the library of formal language tools like Lean. So the value addition here is, and the final goal before I get to the value addition, is that you want the system not only to generate proofs, but also generate concepts and definitions. Because as you well know, in mathematics, perhaps the most important activity is to get the right definition. And my favorite example, I hope the complexity theorists will appreciate this, is the proof of undecidability of first order logic. If we go back to our complexity or computability class, the way Turing proved that was he somehow conjured up the concept of Turing machines. I don't know how he did it, but somehow he came up with it. He showed that the halting problem for Turing machines is undecidable, and then did a reduction from that to the validity problem for first order logic, and thus proved first order logic is also undecidable. Had he not come up with that definition, I don't know how else he would have proved it, right? Maybe there is another way, but it's not clear. So definition synthesis is also an amazing, this creative activity that mathematicians do. I don't know how successful we can be in that space, but it could be very useful, at least as a debugger, if not as a sort of generator of definitions. And the value addition here is, I guess I don't have to make that, but anyway, allow me to do it, is the formalization of proofs is so critical in my opinion, because a lot of proofs out there either have soundness issues with them or completeness. By completeness, I mean that they have gaps in them, and soundness, I mean that they have outright errors in them, okay? Meaning that they violate some previously known facts. So, many tools have been proposed in this space already. You're probably very well aware of alpha geometry and alpha proof, although they don't quite do auto formalization, and they do some sort of proof synthesis, but not in the formal language. You have DeepSeek Prover 2. I think DeepSeek, again, is not doing auto formalization. You have the Gödel Prover, and you also have Lean Dojo, Reprover, and so on. Okay, so what is the idea that we're proposing here? The plan is as follows. We want to give as input to the system textbooks in mathematics with potentially incomplete proofs. There will be an informal reasoner that will reason about it and produce structured output. The structured output would will still be in informal language, but it'll be more structured, like lemmas and theorems and so on, as opposed to, one can expect that chances are that these proofs that humans write tend to be highly unstructured, right? So we want to produce this output structured lemmas and proofs. And then you have an auto-formalizer. And the auto-formalizer translates these to lean. Now, when you do this translation from informal to formal, the good thing about this is that the formal object that is generated can be given to lean, and lean will tell you where the errors are. And chances are that the translation has many missing pieces in it. So there's a lot of missing math in it, right? Because we just assume things to be true, or we just don't write certain parts of the proof. There are gaps in the proof, and we as humans are not even aware of it. And so how do we solve the missing math problem? You can set it up as a search problem. So the way to think about proof search is as follows. At the end of the day, as I said earlier, proofs have two main components in them. One is definitions, and the other are rules, deductive rules, which we call as tactics in the lean setting. And if you have the right definitions, then you could reduce this to essentially a search problem where you search for tactics in the space of tactics and try to construct a proof, and use similar ideas to ones that I mentioned earlier to prune the space of tactics. And again, you provide feedback via RLSF or similar techniques back to the auto-formalizer and informal reasoner to correct the objects that they're producing, and thus continue to improve their quality. And there's one important bit that one has to be aware of here, which is the following. When you translate from informal to formal, you want to make sure that the statement that is produced in the output is indeed the same statement that is given to you as the input, because it's possible that the auto-formalizer might produce a statement which is some trivial statement, and lean can quickly come up with a proof for it, and that won't correspond to the statement that was given as input over here. So that's a serious issue. And at the moment, we don't have any good answers for that, other than to say that the users must formalize the statement of the theorem. The proof doesn't have to be formalized. And the value addition of that is that if I know the statement that is being given to me is in formal language as input, I can then check its equivalence with the statement that is produced, the formal statement that is produced at the output. So in this way, I can know whether or not the output being produced is correct or not. Is that making sense? Yeah. So in conclusion, I started this journey by talking about automated reasoning tools, in particular SAT solvers, and reinterpreting SAT solvers as this reinforcement learning loop, actor-critic loop. The difference between that and the work that people had done in the SAT solving setting previously is that the heuristics that they were developing were sort of ad hoc and not well, shall I say, grounded, if you will. But this allowed us to ground it in reinforcement learning algorithms. And the difference with respect to traditional reinforcement learning algorithms is that they tend not to have logical reasoning in their environment. And this whole idea of producing a certificate and then using that certificate to guide the reasoner, at least it seems new to me. And this had a big positive impact in the SAT space. Today, most SAT solvers are ML-based. They use either my technique or similar techniques. And then we lifted this idea to fine-tuning LLMs with the reinforcement learning with symbolic feedback technique. It was a very natural lift once we realized that LLMs are being used to generate formal objects. And we applied it to chemistry tasks, code synthesis, and logic puzzles. And now we are applying this to generating new theories of physics by combining LLMs with physics simulators. And I also talked about code translation, going from Java to Python and Python to Java, and using a very similar feedback mechanism. And finally, I talked about our future work where we plan to combine LLMs with symbolic reasoning systems like Lean for proof synthesis, auto-formalization, and perhaps definition synthesis as well. With that, I'll end my talk, and thank you for your attention. Please.
Sure. I really like your framework, as you might guess. But as scientists, we want to come up with frameworks that are as general as possible. And I really want to explore or ask, do you believe that there are other instantiations of the framework that might have the same power? In particular, could we replace the reinforced learning part with some other techniques for learning search control expertise? Because there are plenty of them. Some of them go back before the reinforced learning movement really got launched in the early 90s. And could we replace the large language model with some other large source of content, like say the psych knowledge base? Things like that. Now, I'm not saying that psych is going to give all the same results as LLMs. What I'm asking is, it seems to me your framework is not limited to these particular ways. And in fact, some of the other approaches for learning search control and for representing large bodies of knowledge might be more easily integrated with your formal reasoning methods.
Absolutely.
So what do you think?
Absolutely. I'm totally in favor of that, actually. And I think in particular for math, I believe that what you're proposing would be very valuable to have a knowledge base, which is either being used as a feedback mechanism, or even imagine like the knowledge base is somehow being used to generate things. So one of the ideas that we are exploring right now with regard to concept generation is we want to have a system that allows me informal reasoning. So I want to sort of query the knowledge base saying, can you tell me, is there a similar concept to the one that I'm stating here? And that could be like a graph isomorphism sort of check, right? Yeah, and it doesn't have to be perfect, right? I mean, I just want some ideas. And within that setting, either using that as a feedback mechanism or giving it feedback using some formal object just to know what the differences are. Here is one definition, here is another definition. They're not exactly the same, they're different looking, and here are the counterexamples at different.
We have lots to talk about, and I look forward to meeting you.
Yep, thank you so much, yeah. Yes, Pascal.
So thank you very much for the presentation. So when you look at solve, one of the things that they are really good at, is why they work so well, is that they generalize the content.
Correct.
They generalize it so well that you can remove entire regions of the system.
Yep.
So I think, do you think that you could actually go by doing the approach that you have to actually get something which is much more general than actually giving just token feedback, because it's a very weak signal that's going to send.
Absolutely. I completely agree with that. And you can imagine having some sort of LLM style tool, which is more flexible than like a lean. Lean is formal, so all it can tell you, it didn't compile, here is the bug. But LLM could potentially go from erroneous traces to a more general erroneous trace. You can learn such a function, even if you can't code such a function directly. So, and that could provide that kind of a signal. So I do believe that there is great opportunity in the direction that you're suggesting. Yeah. Yeah, Satosh.
Please, go ahead.
Is it clear that you need a reasoning system? I mean, what happens if you only, is there a lower bound saying that if you only have learning, you don't have formal way to provide reasoning, this cannot work? I mean, is it
great? Yeah. I've been thinking about that question myself. So can I prove a lower bound that says that neither learning nor reasoning can solve a certain problem, but the two together can solve it effectively? I don't have a lower bound at the moment. I would love to prove such a lower bound. And if you can help me prove that, I'd be very grateful to you.
It may be false.
It could be false, but my intuition tells me that it is true. I don't know the answer. I talked to Stephen about this, and Stephen came back to me and said, here is a trivial problem that, there is a trivial problem, by the way, Stephen, we can discuss this offline, where, and I don't remember it right now, otherwise I would have told you. But Stephen had this very trivial problem where he said that, where he showed that learning alone or reasoning alone don't cut it, but together they cut it. But it's not interesting. It's like, it's a degenerate case. We want to show some really interesting problem that has this property. And people have, in the last 5-6 years, written papers where they have talked about combining learning and reasoning through a reinforcement learning loop, very similar to what I just said. They call it oracle-driven reinforcement learning, something like that. But they develop a framework of how to think about it, but they don't prove any lower bounds. They don't prove theorems of the sort that we are thinking about. Yeah. Yeah.
So last week, Google announced L5OPT, and I was curious if you had a chance to look at that yet and how that relates to what you presented.
Yeah. And, you know, so first of all, you can think of AlphaEvolve as a generative system that takes its input, some explanation of a problem, and produces algorithms. I mean, that's the claim they're making. In particular, I am already working on a project where my goal is to test these systems to see whether they can generate a SAT solver. Yes, I will naturally gravitate towards that. And one of my students is interning at Amazon, and he's working on a very similar framework, not AlphaEvolve, but similar framework, where the goal is to generate branching heuristics for SAT solvers. So, but your question was, is there a way AlphaEvolve could benefit from this kind of a loop, right? I think that's how I understood your question. And I do believe yes. So at end of the day, when you generate code, you want to make sure that it is doing the right thing. And so you need some sort of a verification system in that setup. And it could help prune the search, right? Now, why not use all help you can get to prune large search spaces, right? Yeah. Yeah, please. Yeah.
I find that like DeepSeek, they have like that RL assisted feedback but it says only a binary reward function. It's like the differentiation, like, oh, for example, if you have like code generation, you say, oh, if I pass 3 out of the 5 test cases, my reward is like 0.6. Is that like the difference?
At the moment, yes. And well, one could make it more sophisticated. With regard to the compiler feedback, we are able to be even more specific. The fine-grained feedback can tell you which, the very first token, which caused the compiler error. And you give it a higher grade to the output if that token is towards the end of the program, right? The closer you're to, the erroneous token is towards the end of the program, the better your program is. I mean, ideally, it's not in the program at all. Does that make sense? So in this way, we can have a very fine-grained feedback. Yeah.
See like a big performance difference between using a binary versus one fine-grained?
Sorry, could you repeat that? Yes. Huge performance difference between fine-grained versus Boolean. Yeah, totally.
So like they have just like another larger LLM providing that.
Yes, yes, and this goes back to the question that Pascal raised. You know, why can't we have actor critics where the critic is another LLM, right? And totally, I mean, I think we should do that, and that LLM could in turn call out formal systems for all you know. So it could be that the first LLM is asked to generate a plan. So instead of saying, generate the code for me, don't do that yet. Generate a plan to generate the code. And then you can debug the plan and so on. Or generate the plan to prove the theorem, which is even more interesting. Like, what is your proof technique going to be? Is it diagonalization or some kind of other type of reduction and so on? Yeah.
Great. Well, let's end the seminar there. Thank you so much.
Thank you.